Hi guys, so this is from Mod 3 Congruent Figures. Number 1, what characteristics are used to prove that shapes are congruent? Alright, all sides are the same length. Well, the corresponding sides are the same, so distance is preserved, I would understand that. Preserves rigid motion, yeah, definitely. Rigid motion, reflections, rotations, translations, um, definitely. They preserve distance and angles. Figures have to translate. That's true. I already talked about that. Rotations are rigid motion. Reflections are rigid motion. Those all preserve distance, angles, all those little things that make things congruent. Angles have to be maintained. Okay, so that's something to note. Dilations, no. See how I wrote no? I'm going to dilate it. No. All right, they do not preserve distance, so they would not be congruent. All right, figures have to compress. Let's say you had your soda can, and then somebody stepped on your soda can. That's not congruent no more. All right, that guy crushed your can. No. One side has to be the same length. Just one side? No, all of them have to be preserved. So, like again, there's your can. Somebody crushes the top of it. Okay, that is not okay. That is not congruent. Okay. Only one angle has to have the same measurement. That is also false. Okay, because look, 90-degree can at the base, and all of a sudden they squished it. Now it's all acute. All right. All right. Number 2, following shape. So you have a rectangle here. Let's say you rotate. Let's say you had an eraser or a block or something like that on your desk, and you rotated it 135 degrees. Then you threw it 2 feet across, and it fell. Or I'm sorry, it fell 2 feet and slid 3 feet to the right of you, and then it bounced and it reflected across a certain line on the floor. Well, let's say you had 22 inches across on the length of that block or that eraser. Well, guess what? It's still going to be 22 inches after you throw it, okay, or you rotate it and do all that rigid motion to it. Same thing with AC. AC is still going to stay 8 when it's A prime C prime. Even after you throw that object, it's that side is going to be the same. All right. Same thing with DB. DB is the same as AC because it's a property of a rectangle, as is DC. So BD is still going to just be B prime D prime, which is the same thing. All right, as AC. Same thing here with D prime C prime. All right. So pretend you had an object. All right, and you threw it across the room. Did all this weird stuff to it. Okay. That was 22. Well, after you throw it and it rotates and reflects and bounces around, moves around the classroom, okay, they're still going to be the same as it originally was. Okay, nobody compressed it, nobody stretched it, the thing didn't expand like a sponge, nothing crazy like that. All right, you just threw an eraser. That's all it was. All right, number 3, figure M and P. So we basically have a situation of like, where did we come from? All right, we have M prime, N prime, P prime, and we know that we went this way. This was our heading. Okay, that's what our translation was. So where were we originally? What was our pre-image? All right, so we got to find our pre-image. That's the situation here. So instead of going to the right 5 and up 4, we're gonna go backwards because we had to figure out where we came from. So instead of going right 5, we're gonna go backwards. So left 5, 1, 2, 3, 4, 5, down 4 instead of up 4, 1, 2, 3, 4. How about that? That is my N. Okay, that's where we came from. If you did the same thing with P, you should be right here. If you did the same thing with M, you should be right here. I'm sorry, M prime to M. All right, so there is your beautiful triangle. If I could ever draw one on this little touchpad. There we go. Okay, so that was your original um, pre-image. All right, moving on. Oh, and they are asking for the coordinates, by the way. So if they ask you for the coordinates, you would actually have to list them out. All right, that is something to definitely notice on your test. If they ask you, definitely. All right, tell them what the coordinates are. There we go. And last but not least, P. There we go. All right, number 4, determine under which rigid motion the figures can be congruent. So I'm looking at P to Q, and it looks like we're just translating along of a certain vector. Okay, so if you wanted to write the rule, if your teacher wanted you to write it, especially in the notation, we went to the right. Let's see, let's double check. We went down 1 and over 4 to the right. Okay, so we went to the right 4 units, and we went down 1 unit on our y. So again, that was a translation. If you look at part B, it looks like we did a rotation. I want to go red to blue, so maybe we rotated. Okay, we rotated. We were in quadrant 1. Now we're in quadrant 3. You can always double check a point. For example, for this point, you were at, it looks like 2, 1. Then all of a sudden, and now it's over here at negative 2, negative 1. And as you can see, that I think that's the rule, right, for a rotation of 180 degrees. All right. Clockwise, counterclockwise, doesn't matter. It's 180. All right. Just spin around either way. You could go this way, or you could go this way. All right. There's several ways you could have gone. All right. Part C, it looks like ABC is staring into a mirror. All right. Here's your mirror. This is also looks like to be your line of reflection. And it looks like a reflection. A reflection across what? Not your mirror. The other mirror in this situation is the x-axis. So across the x-axis. Lovely. And now if they ask you for the rule, if your teacher asks you for the rule, it looks like your x's stay the same, but your y's, okay, they negate. Now, if you look at part D, we had a pink triangle, ABC, and it blew up into a blue triangle, and it was much bigger, twice as big. All right, so this is actually a dilation, and a dilation does not preserve rigid motion. So, does not, that's a P, preserve rigid motion. All right. All right, describe the transformation used to carry the figure KLM to K prime L prime M prime. I'm telling you what, that is definitely going to be on you. That is definitely yours. That's yours for the taking. You could always check a point like K, see where it goes to K prime. So K is at some coordinate, and now K prime went to some coordinate. And you gotta determine the rule yourself. All right, so describe the transformation that can occur there. All right, so we got number 6. Rotation 90 degrees clockwise. All right, so this one's a little tricky. If you remember the rule for counterclockwise 90 degrees, the x and the y, they flip, just like here. But instead of the y negating, it's the x. All right, so let's go ahead and use it for point R. Okay, so point R looks to be at -9, comma, -8. Let's follow the rule. So they flip. Ooh, I'm sorry. Let's see, my y was -8, that's right. And then my x negates, and negative of a negative is a positive. So r prime is going to be at -8, comma 9, right there. Okay, that's going to be for r prime. Here we go. All right, so let's try s. What's kind of funny about s is that it's at -4, comma -4 right there. And if you rotate, it's going to be at -4, +4. That's nice. So if you see that right away, that's awesome. If not, definitely test out the rule right here, and you should see it pan out to -4. Oop, wow, touchscreen, epic fail. Okay, so again, -4, comma, +4. All right, last but not least, t. T was at -3, comma, -7. And now t prime, following the rule, they got to flip. And your x this time negates, so negative of -3 is a +3. So t prime is going to be at -7, comma, 3, right here. And that's t prime. Here I go. The hardest part about this study guide, other than making sure my pen doesn't mess up, is drawing straight lines. Go figure. All right, so that was a rotation of 90 degrees. And that was clockwise. We went that way, like a clock. All right, rotation 270 degrees, counterclockwise. I'll tell you what, get your practice in, try it out. All right, that's homework. Again, look up the rule. You are starting off in quadrant 3. And by the time you rotate 270 degrees counterclockwise, you should be over here in quadrant 4. All right, so that's something to be aware of. Oh, right. So I've already shown you 280 degrees rotations so far. So I'm going to go ahead and make this other part B homework. So again, what's the rule? And then just apply it point by point. All right, number 7. All right, so basically we're trying to figure out whether or not all these situations would work, all these sequences would work, okay? So you have your original figure here, LMN, all right, LMN, and we're trying to figure out if these certain sequences would work, all right, where it would map onto QRS. So let's try it. If we were to deflect LMN across the y-axis, all right, he would turn into this. Boom, boom. N is 5, so it's right here at, I think, -3, -4, -5, right there. Bam. All right, so there would be our reflection. And then it says it translates 0, comma, -4 for our vector. So it goes down 4. 1, 2, 3, 4. Yep, it lands on Q. And then 1, 2, 3, 4. Yep, lands on R. And lastly, 1, 2, 3, 4. Yep, notice our vertices just map perfectly on top of each other. So yes, that guy would work. I'll tell you what, try B for homework. All right, test it. So notice how it's the exact same thing as part A. The only difference is they kind of switched. They switched the order. Okay, so we'll go ahead and test it out, see if it will work. All right, part C. I'll tell you what, I think I'll try part C for you. Let's see. Get it? C. Let's see. All right, rotate 90 degrees clockwise. Okay, let's try that out. So if we were to rotate clockwise, remember the rule that I previously showed you. Yes, they X and Y, they flip, but instead of the Y negating, it's the X. Whoa, look at that. I love the advertisements to the right. I have no interest in sales. What is that? A Lavara? Who puts an advertisement on this thing? All right, there you go. So that's a comma. All right, so let's try it. M is at -1, comma 5. We got a flip. Okay, again, this is for M to M prime. They flip it, negate, so 5, comma 1. That's right here for M. If you do the same thing for L, it's going to be right here. And then N is going to be at -5, comma 3. Yep. So -5 or 3, comma -5. There we go. Right there. There we go. So our triangle ends up right there. All right, and then what is it asking for? Then rotate 90 degrees counterclockwise. Wait, we're going back the way? Oh no, we're reflecting across the x-axis. All right, let's do that. So if we reflect, we're going to be there. We're going to be here, and then I'm going to be right there. Okay. I feel like I'm totally just messing around now. What is this sequence doing to me? There we go. All right, and then now what? So let's see, we rotated, yes. We reflected, yes. And then we rotate counterclockwise about the origin 90 degrees again. If we do that, oh man, we're not going to get there. I want to be like right there, 90 degrees. And then instead of there, I'm going to be up here. Oh man, I don't think this is going to work. That's not going to work at all. Notice how I didn't land where I wanted to, and it looks like I even, oops, there we go, I'm supposed to be there. All right, that didn't work. There we go. So notice my triangle right here. It's not, that's not there. So no, part C did not work out. I was just moving around aimlessly and then rotating in the middle of nowhere. That would not work. All right, D, we got some rotation, reflection, and translation. I want you to go ahead and try testing that out with each other, seeing if that works. All right, you got to map onto QRS. All right, one of my favorites. All right, symmetry and rotation symmetry and angles rotational symmetry. Nice. So we got this beautiful star. So beautiful, I want to use green. Yeah, green. I got one line of symmetry. If I fold it right there, that star is going to map on perfectly to itself. If I fold right here, that's going to work. So I got one line, I got two lines. If I fold right here on this pretty star, it'll map onto itself quite nicely. If I fold right here with that star, well, not exactly right there, because that is the, oh, get out of there. There we go. There we go. And that is 4 lines of symmetry. And last but not least, if I fold here, that is 5 lines of symmetry. So we got 5 lines of symmetry. Now, angle of rotation, well, we got 360 degrees in a rotation divided by 5 lines of symmetry. That'll give us 72 degrees. Okay, so that is our answer for that part. Now, all the angles of symmetry less than 360, so basically all you have to do is if I rotate it once, that's 72 degrees. If I rotate it again, that's 144 degrees. If I rotate it another time, let's see, that's a 6, what, 216? 216, let me do the quick math in my head. Carry the 1, yep, 216. And if I rotate it again with 72 degrees, that's 216 plus 272, and that sounds like that's 288 degrees. All right, and if I rotate it one more time, that'll actually get me 360. But remember, we're going to be less than 360, so we're not including 360. So these are all our angles of symmetry. Rotational symmetry, let's say that. All right, next problem. We got a rectangle. So I want you guys to do that for yourselves. All right, same thing with this square. Try that out. All right, get your practice. All right, number 9, find the sequence of transformations that will map A, B, C, D to E, F, G, H. Write the coordinate notations for your sequence. All right, so if you were to do this, I can see myself doing several different sequences. All right, there's more than just one correct answer. One thing I know right away is if I rotated this just 90 degrees, all right, if I did that, I know that if I rotated 90 degrees counterclockwise, I'd end up right here. All right, you could always apply the rules and see how you can get to where. A would be right here, B would be right here, C would be right here, D would become right here, and of course these become A primes, B primes, C primes, etc. And then basically, so that was a rotation, 90 degrees. And then all of a sudden I notice if I just translate with a given vector, it would work. So my sequence would be thus. You have your original point. We got to rotate 90 degrees counterclockwise so that they flip and the y negates. And then last but not least, whatever your x is, whatever your y is, it looks like we go through a vector, and if we double check from D to H, it looks like we go 1, 2, 3, 4, 5 to the right. So x plus 5, whatever your x value is, it moves to the right. And then 1, 2, and then we go up 2 on our whatever our y value is. And that would be our sequence. All right, part B is for you guys. Try that one out. See if you could do rotations, reflections, even just a whole bunch of translations. Again, sequences there's so many different ways you can get there. Just got to figure out how it matches on. Now, I just want you to know that A, try to map it onto E. All right, and then B, try to match it onto F. All right, so just be aware of the corners, the vertices. All right, let's see, number 10. Determine whether ABC and MNP are congruent. If you test the side lengths, looks like the lengths are all the same or similar or congruent. And BC looks like it's the same as NP. You could always double check the distance formula, or if you remember a Pythagorean, right, for the distance formula, that's by 2 and 3. Well, this guy is also by 2 and 3, therefore AB is congruent to MN because they have the same distance. You could do that with all the others. And even visually, you could just look at it and go, yeah, those guys are congruent. Okay, so, yep, they're congruent because, again, AB is congruent to MN, and if you just double check all the sides, if you double check the angles, they would all be congruent, okay? All right, part B. If you look at part B, okay, this side from A to B is 3, 6, length of 6, okay? And then from B to C is a length of 4. Well, NP, or M to N, that's 4, but their base is 3. All right, that means that this side is way bigger than this side, okay? So no, these guys are not congruent, okay, because they don't preserve distance, all right? If you also look at number A, you can also say it looks like a translation in your explanation. So you got a translation, and translations preserve rigid motion. If you look at part B, it doesn't. It looks like it got stretched or compressed. It looks like compression, all right? So it looks like somebody translated it, but squeezed it through a black hole or something and just crushed your triangle. All right, number 11. Find the given side lengths and angle measurements. All right, so let's find JH. JH should be congruent to EF. So if EF is 31 feet, JH should be 31 feet. They should be the same. Distance shall be preserved because they tell us right away these two triangles are congruent. All right, so what's the measurement of the angle of D? Let's see. All right, D is going to be congruent to angle JGD or JGH. Man, alphabet is tough. I'm kidding. All right, so angle D, 43 degrees, because, again, angle JGH is 43 degrees. That angle is congruent to that angle. All right, they're corresponding parts. All right, number 12. Find the given side length or angle measurement. So we have to find the measure of R, this guy right here. Now, this can be a little tricky, so let's try to look at the sides to get our sense of where we are in relevance to our, not a parallelogram, our quadrilateral. So QR looks to be like the shortest side of that quadrilateral, and LM also looks like the shorter guy. And then the base for this guy, which also looks to be the longest piece, is the longest piece right here. So notice how our angle that we're looking for is in between the two that I was just focused on. Well, it looks like angle R is corresponding to angle M. Now, if angle M is 79 degrees, angle R is also 79 degrees, all right? Because they tell us right away that these two quadrilaterals are congruent. All right, moving on. PS. All right, PS is this uh, other side here, which looks like to be corresponding to KN. So if PS is, again, congruent to KN, all right, that means, well, KN is 21 or 2.1 centimeters, so PS should be the same, 2.1 centimeters. Please pay attention to the units. Make sure you don't get points docked off you from any teacher. Make sure you understand the context. All right, that looks like it does it. So if you guys have any questions, please let me know, and best of luck.